All right. Welcome. Thanks for coming. I hope you're enjoying NDC. This is my first NDC Sydney. I've been to NDC Oslo several times and London, but it's really fun to be on this other side of the world. My name is Sasha. I live in Israel. I work for a training and consulting company back there. We're on a 3-week tour, holiday, business, vacation kind of thing here in Australia, and we've really enjoyed it so far. So this is profiling Node.js applications, and I'm assuming you have Node.js applications you're building or you're considering to build, and at some point you run into performance problems, or you want to avert the performance problems in the first place. I'm also assuming that you will at some point reach production, and then you'll also have issues in production. So you'll have performance problems in production to debug as well. And indeed, the focus of this talk is mostly on investigation techniques and tools and practices that you can apply not only in your development environment, but also when it hits you in production. So we'll take a look at some techniques that you can use without having to restart the process or add some modules, especially just in order to get some profiling and performance information. So kind of the main objective, if the clicker would work, let's see, there we go. So the main objective is investigating, profiling Node.js applications in production. I'm assuming that most of you are probably using Linux as your production environment for Node.js, right? That sort of makes sense. You can run Node.js on Windows, you can run Node.js on Mac, Smart OS, what have you, but I'm assuming Linux is the one most of us use. So the tools and the examples I'm going to be showing are going to be on Linux, but I will show equivalents, or at least mention equivalents from other operating systems that you can use if you are using those. There's 4 bullets in there that I would like to achieve by the end of the presentation. So I want to tell you about which production-ready tools you can use to profile your Node applications, to get performance data out of your Node applications. I want to talk about CPU profiling, which is a real issue for Node apps, as they tend not to be so good at CPU-intensive work. So figuring out where the CPU-intensive parts are and optimizing them is important. And we'll also visualize this information using flame graphs, which you might be familiar with from other places. We'll talk about getting accurate call stacks for various kinds of interesting events, like garbage collections in your Node.js process, or things that slow down your event thread, like doing synchronous I/O, synchronous file accesses, synchronous network requests, that sort of thing. And we'll see some examples, which obviously are not full-blown actual investigations, but sort of show you what the thinking process is and how I approach, in any way, a typical performance issue from start to finish. And just a couple of words about myself. That's part of what I do. I'm a consultant working on performance investigations, debugging stuff in production for customers across various runtimes and operating systems. And so this is sort of what I do, and I really like telling other people about it as well. Before we dive into the tools, there's some introductory sections that we have to cover. This is something I put on all my performance talks, and that's mind the overhead. So if you have any kind of performance tool someone recommends or someone puts online, you should not right away run it in your production environment. A lot of tools, especially tools that call themselves profilers, tend to have a really considerable overhead on your system. So you might be able to run them in development, but you shouldn't probably run them as is in production. So again, having that background of doing performance investigations in the field, I do tend to be very wary of this sort of thing, and the overhead certain performance tools have. So the tools we'll be talking about mostly are very suitable for production use, but you should absolutely not trust my word about it, and you should really test in your own environment and see if that still makes sense for you. And for example, a lot of CPU profilers, they work really well if you put them on a box that has 4 or 8 processors, but then all of a sudden you have a box with 256 processors, and then the CPU profiler becomes the bottleneck and just brings your whole environment down. So it's really something you have to test. Another piece of theory that I want to get out of the way is the difference between sampling and tracing tools, and then we'll start looking at specific examples. So a lot of the things we'll be doing today are based on tracing a certain kind of event that happens in the Node.js runtime, in your JavaScript code, in the operating system code. And some events are sufficiently low frequency, they happen rarely enough, that you could actually record every single event. So for example, garbage collections for most node processes would probably happen a couple of times per second or something like that. So you can record every garbage collection to a file and analyze that later. But for some events, they're so high frequency that you simply can't record every individual occurrence, and that's where sampling comes in. So instead of recording every single event, you sample and just record every 10th event, every millionth event, every billionth event. So you only have a statistical picture of what's happening and not each individual event as it occurs. So we'll be using tools from both flavors. For CPU profiling, for example, tracing is pretty much impossible, and sampling is the only thing you can use because you can't trace each CPU instruction as it gets executed. So in terms of operating systems and sort of the scenarios we'll be looking at, there's 5 major things. So we have CPU sampling, we have dynamic tracing, by which I mean attaching to various interesting functions in the Node runtime. We have static tracing, which I'll explain when we get there, but Node is instrumented with a couple of interesting markers that we can monitor for interesting information about HTTP requests, garbage collections, that sort of thing. There's also a bunch of different monitoring tools, more lightweight monitoring tools that depend on the OS. And there's the V8 profiler, which we'll actually start with, which is built into the runtime, built into the Node.js runtime, which is V8. And so there's rough equivalents for most of these things on non-Linux platforms as well, but we'll be focusing on Linux. The rest is just to give you an idea of what you'd do if you actually had to do it on a different OS. So mostly it's the same principles, it's just going to be a slightly different tool. So let's start with the V8 profiler. And I'm going to do a mix of demos if I have time, and just slides that have all the demo steps. So it's really going to depend also on the questions you ask, if any, and how much time we spend on each demo. So the first scenario we're kind of going to attack is a high CPU Node application. So we have a Node app running, and all of a sudden there's high load, and it's consuming almost 100% CPU, and we want to figure out why, what's taking so much CPU, why the sudden change maybe, and actually nail down the piece of code that's consuming lots of CPU. And we're going to use the V8 profiler for this. And this is actually borderline acceptable for production use. And I say borderline because using the V8 profiler does require that you launch your Node process with a profiling flag up front. So it's not something you can do with no additional configuration, just grab a random Node system and attach a profiler. You have to run Node with the prof command line switch. There's also another option, which is to start with the profiler disabled, and then call an API, use a JavaScript module to start and stop profiling programmatically, which is also reasonable, but it, again, does require some changes. Maybe you'd have some kind of secret endpoint that would start profiling, and then another endpoint that would stop profiling and get you the profiler results. So these are all sort of feasible options, but it's something that's, again, borderline acceptable for production use. So how the whole workflow works for the V8 profiler, you start by launching Node with the prof switch. You exercise the application, you run the performance scenario we're interested in, and that generates, the runtime actually generates log files, pretty massive log files that have a bunch of stack traces for what the CPU is doing inside your Node process. And then you run Node again with the --prof process switch, which reads the log file and generates a report. So I'm going to try and show you a quick example of this. So over here, I just have this really tiny web app that actually I have a run script for. So that's just run sh is a little script I have that runs the process, sets it up. And now we can issue requests. So I'm going to specifically request localhost 3000 users authorize, and I'm going to add quotes here. Authorize, and yeah, I don't actually remember the whole thing. Let's see if I have, oops, sorry. That went away. User's auth is what I need, and then username foo, and password goo. Now let's sort of set aside the fact that I'm passing the username and password as query string parameters. Let's sort of totally ignore that. But then when I actually hit the page, it returns an error. And sorry, let me just, for 1 second there, make sure that I'm actually using the right thing. So users, oh, it should have been a post. Yeah, so that's it. So -x post. OK, so that returns unauthorized, which is what I expected. And I mean, it's sort of sensible, so I try to authorize with an invalid username and password, and that returns an error. But people are sort of complaining that the whole thing is kind of slow. And on a particular server, I might be having a flood of these authorization requests that are slowing the server down. So I could maybe run a benchmark, like issue 1,000 of those in 10 concurrent requests, and using the post method, and then just the same thing, users, auth, username foo, password goo. So let's just run this thing for a moment. So that's AB just running the benchmark. And it's fairly slow, I'd say. It's supposed to print, I think, every 10% completed, right? So I only asked it to run 1,000 requests, and only now it's got through 100. And I mean, it's not a super powerful box, but still, I'm expecting a somewhat higher rate. If I just hit Control-C, you'd be able to see my statistics here. So my median request is 1,100 milliseconds for a single authorization attempt. And that's suspiciously slow. And also, while this benchmark is running, if I just run top for a moment there and resize to make room for the process name over here, you'll see the node process taking, well, almost 100% CPU while the benchmark is running. So that might be expected, might not be expected, but it seems that we have a very, very busy server here that's being overloaded by these authentication or authorization requests. So here's where you'd use the node profiler, especially if it's something you can so easily reproduce in development. So this is where the node profiler works best. And I'm going to kind of skip through the steps and just show you the general process. So again, like I've done in the demo, I've run top. And then you'd run node with the --prof switch and repeat the experiment. And that produces these gigantic log files. And then you run node with the prof process switch like this, and just pass in the log file. And that generates a huge text file, a huge text report. And so I've sort of removed the irrelevant stuff and just kept the important parts of that report for our purposes. So it begins with this summary over here that says that 96% of my time is actually spent in C++ code. So not actual JavaScript at all, but C++. Now C++, as you know, if you have a Node app, C++ can only come from two places. It's either the runtime itself, or it's some native module, right? It's some module you're using that has a C++ component in it. Now, in the C++ section, specifically in the report, you'll see the hottest functions, and then you'll see that 93.5% of my C++ functions is actually this one function here called crypto pbkdf2. Now, I don't know if you're exactly familiar with it, but it's a hash function. It's a function that hashes a sequence of bytes, produces a hash. And it sort of makes sense that we would be doing this as part of authentication, maybe hashing the user's password. And we also have another way to confirm. So this here is the call stack leading to the pbkdf2 function most frequently. And that call stack goes through crypto.js, which is JavaScript code, calling into C++ code. And from my side, I've called pbkdf2 sync, and I've done so over here. So that's users.js line 46. This is where I'm actually calling this pbkdf2 sync function. Now, you might argue at this point that I am synchronously, from my route, invoking this hash function, and I totally shouldn't be doing that. I should do that asynchronously, right? And like, why would I even use pbkdf2 sync if there's a pbkdf2 without the sync at the end? But it turns out, I mean, even if I did do this asynchronously, it wouldn't get rid of the CPU computation that had to be performed. Like, the hashing is still there. I could do it on the event thread, and then it sort of pauses the response from getting there. Or I could do it in a background thread, but it's still, I mean, there still wouldn't be a response until the computation is done. And I couldn't really overlap multiple of those hashing operations because it's not I/O, it's not happening on a different server, it's just happening on a different CPU. So I might try to actually change this code to be asynchronous, but it definitely looks like we're doing a lot of hashing operations per authentication request if it takes over a second per request. And indeed, if we do look at the code for a moment there, so just gonna look in users.js, and then there's this auth route. So you can see over here that I'm actually calling pbkdf to sync. And then this argument over here is the number of iterations desired, and that's 10,000. And that's pretty crazy for hashing a user's password. I don't think we need 10,000 iterations for that. So that's clearly a place we can improve. And I don't know if you noticed, but the report actually gives you the line numbers, right? So not just the JavaScript file name, but also the line number, even the column number where the samples are coming from, where the stack is coming from. So this is fairly useful for identifying busy CPU functions in your code, figuring out what calls them. I should note that the V8 profiler, the way it's currently implemented, it would only profile your event thread, your main thread, your single Node.js thread. If you have additional threads, they can't be running JavaScript, right? Because Node can only run JavaScript on a single thread per process. But you could have additional threads running native code, running modules and that sort of thing, and they would not get profiled by the V8 profiler. So it only picks up the main thread, and it requires that you launch the process with this ugly switch that generates a lot of data into a file. So it's kind of, again, borderline production ready, I'd say, and we definitely want other alternatives. The one thing that this profiler has going for it is it's just built in, it's out of the box, it works on all platforms, it's the default. But you shouldn't just stick to the default, there's better tools coming up. So the better tool coming up that pretty much every talk on Linux performance eventually ends up mentioning is perf. And perf is the Linux tool for performance investigations, especially for CPU profiling of the kind we've been doing so far. It's capable of a lot of different event sources, so it can record CPU samples, it can record context switches, it can record a variety of information about your system, including disk accesses, networking, and that sort of thing. Perf is developed as part of the Linux kernel tree, so it's just sort of aligned exactly with the Linux kernel you're using, and you can install it from your packages, from your package distribution. For example, on Debian systems, it's usually in Linux Tools Common. On Red Hat, it would be in the perf package, so you can install it and then start using it. Now, for a node process specifically, there's a certain challenge with using perf that we'd have to overcome. So again, the objective is going to be the same. We have the same process with a heavy CPU usage, and we want to figure out where the CPU usage is coming from, but we don't want to launch the process ahead of time with a profiling flag and go through the whole process. We want to attach to a live running application and extract information out of that. So here's what the demo is going to look like here. Again, I might run through it live a little later. So it starts with perf record, which is the basic verb for recording CPU samples and recording actually a lot of other kinds of events that perf supports. And then we have, importantly, it requires root, unlike the V8 profiler. Perf mostly requires root. You can sort of get it to work for an individual process without being root, but you need to make sure certain things are configured properly. So if you want to go there, talk to me later. But for now, we're just going to assume root. Then there's a process filter, which tells perf which process you care about. So that's just going to be the node application. This is the frequency with which perf is going to look at that process and see what it's doing. So it's going to grab samples of what the process is doing. And finally, the gswitch is for stack traces. So just in addition to the current function, take a stack trace of which function called that other function and so on. So we have a complete tree of functions and not just the current one. So you run a perf recording. And then you run perf report. And perf report is supposed to display this user-friendly summary to the terminal telling you which paths in your code were the hottest. Kind of like the V8 profiler over here, which gave you a report of which functions were the hottest ones. That's also the same thing that perf is supposed to do, except it would probably look like this. So it would have a bunch of numbers, really, really many numbers, possibly hundreds of screens full of these numbers. And all of these things are actually JavaScript function names, but perf doesn't know it. As far as perf is concerned, this is just arbitrary addresses in memory. And the reason for this is, as you know, Node employs a just-in-time compiler. So your JavaScript code is compiled to CPU instructions at runtime. And that translation, that compilation, is totally unknown to perf. Perf doesn't know how to translate the just-in-time compiled function addresses to function names in JavaScript. There's the same problem exactly if you are using perf to profile Java apps on Linux, .NET Core apps on Linux, which I gave a talk about today. Virtually any runtime that is not statically compiled ahead of time, like C++, would have this problem. So the way to resolve it is to run Node with a magic flag. And now at this point you might say, I mean, this also needs you to run Node with a magic flag, so what's the advantage compared to the built-in profiler? Why are we even talking about this? The major difference is the prof flag, which we talked about before, that starts profiling right away and starts emitting huge amounts of information to a file. This flag here, the perf basic prof flag, instructs the runtime that whenever a method is getting compiled, whenever a method is getting JIT compiled at runtime, the method address and name are stored into a file. So it's not actually starting profiling, it's just emitting some supporting information. I can show you the file in a quick demo over here. So if I just get out of Vim, and I run Node with --perf basic prof on that particular app. Oh yeah, I have to kill the existing one first. Okay, so now if we look in temp, there's actually two of them from another experiment probably, but there's this map files that get created. And let me show you what a map file, what these map files actually look like. So let's go to perf pit of node.map. That's what the perf map files look like. So there's an address and a function name, an address and a function name. And this might not look like JavaScript. It's some internal V8 implementation details. But at some point, we are going to get to JavaScript as well. So here we go, right? Buffer.js and errors.js and collection.js and so on. So this file that gets emitted by the Node runtime has the translations between function addresses and function names. And perf is able to pick up that file automatically with no further instructions from you. It just goes ahead and looks for that file, reads the data, and then puts it in the report. And then the result looks like this. Rather than addresses, we now get a clean call stack which has all the functions we previously saw, like pbkdf2 sync, pbkdf2 in crypto, so that's all the same stack we saw before. However, I'd say for a real app that has more than just one hot path, this approach, where you browse through a bunch of text in your terminal, is not going to scale very well for you. The V8 profiler suffers from the same problem. It spits out a huge report that you now have to read. We clearly need a way to visualize this information, regardless of its origin, right? So it's just, it could come from perf, it could come from V8, it could come from some Windows stack tracing mechanism, I don't care. I have a bunch of stacks leading up to my hotspots, and I want to visualize them. And that's where flame graphs are going to help us. So for the particular example I used in the demo, if we actually went through the whole report that perf produced, that's 18,000 lines. So nobody's going to read that. And that's for a very, very simple application. You could easily get hundreds of thousands of lines to go through if you keep persisting with the text-based approach. So we're going to use flame graphs for this. And flame graphs, if you haven't seen them before, is just a visualization method for stack traces. You have a lot of stack traces leading up to a certain hotspot in your code, and you want to put them in a single diagram without having to wade through screenfuls of text. They were invented by Brendan Gregg for this purpose, and they can be used for CPU sampling and for a bunch of different things. We'll see flame graphs later in a totally different context for identifying off CPU time and not actually on CPU time. It's also going to be useful there. Now, how do you read one of these things? Rather than the slide, I just want to show you a quick live example. So this is a flame graph generated from a Node.js process. First and foremost, ignore the colors. The colors are just there for prettification, right? So the whole thing is a little easier on the eyes, or not, arguably. It's just there to differentiate the different functions. So the colors are totally random, and they are designed to make it look like a flame, hence the name flame graphs. Now, each rectangle you see here is a function, right? So this is pbkdf2 in crypto.js. This is pbkdf2 in the C++ V8 code. This is users.js line 85, and so on. So that's just JavaScript functions and C++ functions. Each rectangle is a function. The vertical axis is the call stack. So if you have, for example, over here, you have users.js line 85, and then pbkdf2 sync in crypto.js, it means this one was called by that one. So it's just the stack growing up. That sort of makes sense? Then we have the horizontal axis, and most of it is just currently one rectangle, but then towards the top, we have some splits, right? So the horizontal axis is just alphabetically sorted. It's not a timeline or anything. Chrome developer tools, there's a very similar chart in there called a flame chart, and it's not a flame graph, right? So a flame graph and a flame chart, totally different things. A flame chart actually has a timeline component to it. This doesn't. This is not a timeline. It's just a summary of where you spend time in general. And finally, the wider something is, the more prominent it is. So you should immediately look at the widest towers in your flame graph. So in this example, it's all pretty much leading to the same place, which is here, pbkdf2 request work. And that ended up calling a couple of internal functions, which also called a couple of internal functions. But that's just, that's implementation details for the Node crypto module. I don't really care about those. My code pretty much ended 10 frames previously up the stack. So this is just a way of visualizing a stack trace. Now, this is actually a zoom into a larger flame graph where this was just one tower, and I've zoomed into that tower, but there's also another couple of towers at the bottom there. And there's even this tiny tower, which I'm not sure where it's coming from. Yeah, so that's also coming from Node, which called syscall. That's how Node waits for events. So given a flame graph, you can obviously zoom in on things. You can even do a search, like I could search for crypto here, and then it's going to highlight any frames that have crypto in them. So that sort of helps navigate the whole thing. You can put a file name there. You could put a module name there. It's going to help you navigate through the flame graph. So how do you make flame graphs like that? One way, which is totally not Node.js tailored, it's a totally generic way, is using a script called flamegraph.pl. It's a Perl script. There is also a couple of more native Node implementations. There's one called OX. There's also one called StackViz. There's a bunch of options. They all produce the same thing, virtually the same thing, that diagram that shows you the hottest stacks, the hottest call stacks in your code. So again, here's what it might look like. For our example, again, we just saw the same thing in the browser. pbkdf2 is the hottest frame. And the way we generated this, if you look at the top, is just by running perf script and then feeding the output into a couple of Perl scripts which produce the final result, which produce the diagram. And the diagram is an SVG illustration, which you could obviously load in any other browser. So we just saw how perf improves upon the process by letting us attach to a live running process, capture what it's doing, capture a profile, and then analyze it and produce a flame graph, there's still a major deficiency, which is why I'm going to introduce you to yet another tool, to yet another approach of profiling Node apps on Linux. And to understand what's wrong, you have to consider high-frequency events. So the way perf works, basically, is that it records a lot of events very quickly into a file and passes that file to a user space application, to a script of some sort, to do the actual analysis. In our case, it might have been generating a flame graph. In other cases, it might be a text-based histogram, illustration, whatever. But you have to go through a file to user space. So if you have a high-frequency event that you want to record like this using perf, you're going to run into bandwidth issues with your disk. So I did an experiment on an AWS EC2 instance. I downloaded a file over a 1 gigabit per second link. And while I was downloading the file, I used perf to capture events for each packet getting received. Now, not the packet data, right? So not like a network sniffer. I don't care about the data, just the raw event, the fact I got a packet. I wanted that recorded. So I had a rate of approximately 89,000 events per second. And that produced a log file, which grew at 19 megabytes per second of log data. So that's a lot, obviously. If you have a not super fast disk, it could actually saturate your disk. Just the profiler itself, writing profiler data to a file, would saturate your disk access completely, or at least slow it down a lot. Needless to say, you need a lot of disk space for 19 megabytes of second worth of data. If you plan to record for minutes or hours, it's not going to scale. So this whole approach where you record everything and then you analyze it later, you do post-processing, that's an unreasonable approach, I'd say, for certain kinds of events. And just to sort of get ahead of myself, the next thing we're going to be doing, like the next scenario, is going to be identifying blockages on our event thread. Like, why is our event thread getting blocked? Maybe on I/O, maybe on network access, maybe on something else. And to get that information, we would need to record context switches. Whenever our event thread switches out of the CPU and goes to sleep, we would need to record that event. And on Linux, you could totally, on a very reasonable production system, you could totally get millions of context switches per second. So if you record every single one and plan to analyze them later, it's just not going to scale, not even for minutes, not to mention hours or days. So to do that kind of investigation, you do have to process events in real time. You can't keep every single event. You have to process them in real time and discard them. And this is where we need to introduce a new technology. And that new technology is BPF. It's not Node.js specific in any way, but we will obviously use it for Node.js application profiling. So BPF was invented as a packet filtering technology. If you've used Wireshark or TCP dump or Tshark, all these different tools, you've used BPF. It's a language used to describe packet filters. It has nothing to do with performance tracing whatsoever, but that's where the story begins. In recent Linux versions, BPF can be used not just for packet filters, but also, surprisingly, for high-frequency processing of events coming from the kernel. So it could be events like CPU samples, it could be events like context switches, it could be events like disk accesses. So you could use BPF to process at a very high rate to process events in the kernel where they arrive. So just to contrast the two approaches, on the top, you have the perf approach, where you have some kind of data source, regardless of what the data source is, but you have something pushing events into the system, and then perf would produce a data file that you then have to analyze and get some kind of report or monitoring data out of. So this could be a flame graph, this could be a histogram, whatever. With the BPF approach, you don't have to store and pass forward every single event. Instead, you have a BPF program that runs in the kernel, and that program performs the aggregation. That program generates the necessary information so you don't have to keep every single event. And then the only thing that goes to user space is a summary data structure, and then you have an application in user space that would display it in some way. So you don't have to keep every single event. That's the main takeaway. Now, you are not actually going to be writing BPF programs yourself. It's just a technology which has a lot of tools built on top that sort of make this possible. BPF is available in Linux kernels over the last 2.5 or 3 years or so. So the only reason I haven't started with BPF in the first place is that you might still find yourself on an older Linux version where you still have to use the perf approach from the olden days. But hopefully going into the future, the perf approach of storing every event is going to be displaced by tools that do real-time analysis instead. And that opens the door to a bunch of interesting things which we can talk about after this session. So the set of tools we're going to be using specifically, just to give you a reference for later, is called BCC. It's a toolkit based on BPF that has a collection of tools, mostly Python scripts, mostly scripts written in Python, for a variety of different performance investigations. Just to give you an idea, there's scripts for Node specifically in there, but there's also a lot of stuff for database engines, for disk I/O investigations, for network investigations of different kinds. There's a variety of tools for everyone there. And it's an open source project that's maintained by a bunch of people. I've also contributed a couple of tools to this project. And it's already used pretty widely by Google, by Netflix, by Facebook. It's BPF and BCC are actual technologies that are getting traction in the wild. So again, we want to use some of these tools to profile our Node.js application. And what I want to start with is just a very, very quick mention of how we could get the same result, right? The same flame graph of CPU usage using the BCC approach. So I'm not going to go through this very thoroughly because it's going to produce the same result, but just to illustrate the difference, the way it works with the BCC tools is you get a script called profile that attaches to the system at a certain frequency, just like perf did, and produces the input for flame graph generation. And it looks pretty similar to what we did with perf, with the key difference being that the aggregation of call stacks happens in the kernel. So rather than store every single event, there is a BPF program in the kernel that's doing real-time accounting. So we have seen this call stack 1,000 times. We have seen this call stack 2,000 times. We have seen this call stack 3,000 times without recording each individual sample to a file. So again, the output might be very, very similar, but the approach used to generate this output is totally different, and the overhead difference can be an order of magnitude. So it can really lower your overhead when running on a production system. And additionally, it of course saves you the disk space. You don't need to store these huge perf data files. So the next thing we're going to do is what I promised you in the first place. We're going to look at off-CPU profiling, so identifying situations where the event thread, the main JavaScript thread in Node, is stuck, and not by CPU work, but actually waiting for something, sleeping, doing synchronous I/O, something blocking that doesn't let the event thread handle additional requests. And we're going to use a couple of tools for this from BCC. The first one is going to be off CPU time. The other is going to be file slower. Let's just take a quick look. So here's sort of a summary of our initial findings that lead us to this investigation. I've got a certain endpoint called stats on my Node service, which produces the following tiny JSON document, not really interesting. But then I ran a benchmark, and looking at the benchmark results, I can see that my mean response time was 116 milliseconds from that endpoint. But on the other hand, I can see that the CPU was not very busy. The CPU was at 35%. So, and for some reason, right, I expect a higher rate of requests. I expect to be able to handle a request in less than 116 milliseconds. So this is what leads me further into the investigation. Now, we could use a CPU profiler now, like the V8 profiler or perf, but it would only show us what's going on in these 35%. It's not going to show us the rest of the time where we are not using the CPU, but rather blocking in some way. And this is fairly tricky. Like if you look online on how to figure out why my event thread is blocked, it's not trivial. And a lot of the solutions involve adding code or adding modules that would do some kind of instrumentation, which is totally non-trivial for production use. So what we're doing here is just using a tool from BCC called off-CPU time. It's designed for exactly this situation, where you want to figure out what you're doing off the CPU while blocked and not on the CPU while running. And we point it at the node process, and we instruct it to generate a folded stacks file, which is basically input for flame graph generation. So we could just feed that into a flame graph generation script and get the following flame graph. Now, it's not actually an interactive flame graph. It's a screenshot on a slide, so I can't zoom in like I did before, but we can manually zoom. So this whole section on the right, there's something here, but it's fairly narrow, so I'm just going to ignore it completely and look only on this side here. So there's this major tower over here going all the way up to the top. And if I look at at the bottom of this tower, it says over there, index.js line 73. That's something in my code. And what it seems to be doing is closing a file or something similar. And so this code is still in V8. So node close, UV, FS close, that's still C++ in V8 in the node runtime. But then this whole section going all the way up, that is kernel code. That's kernel functions in Linux. And if we look at these functions a little more closely, again, we're not kernel developers, we're not supposed to be, but the function names are often pretty descriptive. So first of all, XFS is, of course, our file system. XFS is the extended file system. And then if you just look at the function names, it looks like we are, over here, flushing a file, and that's happening while closing the file. And there's a lot of stuff here with bitmap write and log allocate and that sort of thing that's happening inside the file system. So this is all what happens when you close a file that you previously have written to, and then the file system has to flush your changes to disk. So that happens here upon closing the file. But that's sort of not the point. The point is that we are synchronously closing that file and blocking the event loop, because this is all happening, again, from index.js line 73. If we had done this asynchronously, we wouldn't be blocking the event loop while closing the file. So this is clearly time spent in synchronous file I/O. And if we go there to index.js line 73, I don't know if it's actually 73 still, but let's see, just look for sync. Yeah, so here it is. This is the stats endpoint. And as you can see here, what it does is just it calls write file sync. And write file sync internally does, of course, close the file as well, synchronously, because I ask for the whole thing to happen synchronously. And only after the whole thing, I return a response, and that's all happening on the event thread and blocking it. Now, I know it's not a very realistic scenario, but that's not the point. The point is that we were able to look at a totally arbitrary process and figure out what's blocking the event thread and maybe what we can do to unblock it. Now, of course, in some cases, you just see that the event thread is as busy as it can be, and there's nothing you can further offload. But in a lot of cases, there is a bunch of stuff you can move away from the event thread and speed up your rate of event processing. So that's an example of off-CPU profiling that I wanted to show you. Now, once we have that, and we know that we are closing files, writing to files, there's also another tool we could use before heading over to the source code, and that's file slower, also from BCC. And this is a super simple tool. You just point it at a process, and it spits out all the file system operations performed by that process that are slower than a certain threshold. So here, my threshold was 1 millisecond. So it's just spitting out all the file operations slower than 1 millisecond. And so each line here, you can see it has the number of bytes being written or read, the latency in milliseconds, and the file name. So you can do a complete investigations of what files are being accessed by your node process. This is not node specific at all. it's completely generic. This log that the flame graph we got over here, it did require, again, the same map file that maps JavaScript function names to addresses. But otherwise, it's a completely generic technique. OK, next thing I want to show you is the built-in static instrumentation inside Node.js and how we can do a couple of pretty cool things with it. So just as a high-level overview, static instrumentation is about putting static points in your code, in libraries and runtimes, in your applications, that you can later instrument in production and trace. So you could, for example, trace your orders, you could trace your authentication requests, you can trace your garbage collections if you're a runtime, you could trace your module loads or requires if you're a runtime, so that sort of thing. And it turns out there's a lot of this static instrumentation built in to a lot of languages that we're using currently on Linux today. So the JVM has them, PHP has them, Node has them as well. Now, Node itself doesn't have a lot of these, but the runtime, the V8 runtime, is a C++ runtime, so we can find a lot of additional instrumentation points over there, and I'm going to show you a couple of examples. So what we want to do first is just see what kinds of things we can trace in a running Node.js application, and we're going to use a couple of tools for this. Some of them are from BCC, some of them are just Linux tools, like objdump. So first of all, this is a tool from BCC called tplist, which you can point at a process, and it tells you what static instrumentation points exist in that process. And specifically, I've highlighted all the node-specific ones. So you have events for GC start and GC completed. You have events for HTTP requests coming in, HTTP responses going out. This is a set of probes that were put there by the Node developers, so we could trace these events as they occur in production. Another approach, which is only applicable for compiled languages like C and C++, is just look at all the functions in a particular binary, because for compiled languages, we could actually trace any function we want. So this incantation at the top instructs objdump to print out all the functions in the Node binary and then format them a little more nicely. But this is just basically C++ function names from the V8 runtime. Now, you're not supposed, of course, to know what each function does, but if you're looking for something specific by keyword, you could probably find what you're looking for. So here's an example of a couple of things we can do using this approach. This first command here, the trace command, what it does, it attaches to one of these static instrumentation points, in this case, HTTP server request. So whenever our Node application handles an incoming HTTP request, this here is the trace message we want printed. And the arg5 and arg6 look a little magical. You do need to do some spelunking behind the scenes to figure out what they are. I'll save that for later. And there's a process filter as well, like which process do I want this information out of. The output looks like this, fairly simple. And hopefully by looking at the output, you can see that arg5 seems to correspond to the HTTP verb, and arg6 seems to correspond to the requested URL. So this is basically just a way of doing dynamic logging. Just point this tool at a certain application and tell it to trace a message when something interesting happens. So in this case, the attached target is Node.js specific. It's the HTTP server request static trace point. Now we can do something similar with other kinds of points like that, instrumentation point like that. And I want to do it through a scenario, which is identifying excessive garbage collections. So suppose you have this Node process that's doing lots and lots of garbage collections. It's not actually as uncommon as it might sound. Like high CPU load is more common than excessive GC, and probably various kinds of networking issues are more common than excessive GC. But I've seen my share of excessive GC issues as well. You know that Node has a garbage collector, and garbage collectors, they do tend to sometimes do excessive work. And by excessive, I mean they can pause your process while the garbage collection is happening. They can introduce a high CPU load, so basically we're spending time collecting garbage rather than processing useful requests. So that's just stuff that happens if you put too much load on your garbage collector. So we're going to use a couple of tools to diagnose that. So the first tool is node-specific. It's called UGC. It's also based on BPF. And it would print a message whenever there is a garbage collection in a Node application, and it tells you the duration of that garbage collection. So before you start investigating, you can just figure out if you even have a problem before you allocate any further resources to it. So looking at this output here, specifically the highlighted sections, we have garbage collections taking, not very long, because it's in microseconds. So 9,000 microseconds is just 9 milliseconds. But they are happening fairly frequently. Like if you look at the first column here, the start column, that's in seconds. So in less than 200 milliseconds, we had over a dozen garbage collections in that process, each taking less than a millisecond or slightly more than a millisecond, but we definitely have a lot of garbage collections happening. And of course, you could aggregate this information. Just tell me how much time I spent on GC in the last 5 seconds. And then you could get a reply that might say, well, over the last 5 seconds, you spent 3 seconds doing garbage collection. And that's obviously very bad, and you want to figure out why. You don't want to spend most of your time garbage collecting. So what comes useful next is, again, a couple of tools that can do dynamic instrumentation of a node process. So this example here has us using a tool called func latency. And that's a tool that attaches to a certain function and gives you a summary of how long that function took to run. So it can give you a summary of how long a particular function took over an interval of time. And the output, as you can see, is a beautiful ASCII-based histogram. Right? So it doesn't really look like a histogram because there's only one bar that's very big, and all the other bars are kind of not pronounced at all. But it is a histogram, and it shows you that most of my garbage collections, because that's the function I was tracing, most of my garbage collections took less than a millisecond. Like I had 1,900 garbage collections under a millisecond. But I also had 38 garbage collections taking between 8 and 15 milliseconds. And that's slightly more concerning. And in a real app, you might see even longer delays. You might see garbage collections taking up to a full second even, or even more, if you have a large heap that needs to be collected. So given that, you sort of want to discover, figure out where these garbage collections are coming from. Like, what is your JavaScript application doing to trigger so many garbage collections? And there's something else you can do. I'm going to skip this little section here. There's something else you can do to get this kind of data. There's a tool called stack count. And that one will tell you which paths in your code lead up to a certain function. This is very similar, if you think about it for a moment, this is very similar to what we did at the very beginning. We got lots of stack traces telling us what the process was doing in general. But this is no longer in general. I know there's a specific event. There's garbage collections that I care about. So tell me the call stacks leading up to garbage collections. Not just arbitrary call stacks, but only call stacks leading up to garbage collections. And you could actually visualize them with a flame graph as well. If you have lots of stack traces, you should immediately think flame graphs as a way to visualize this information. I haven't done this actually for this example, so it's just text. It's a stack, as you can see, and then a number that says how often, how frequently we actually saw this stack. So this stack here appeared 111 times. That's what it means. And if you look at the stack itself, it has a mix, as usual, of V8 code and JavaScript code from our application. The highlighted sections, specifically, as you can see, point to users.js line 7, which allocates lots of memory by slicing a string. And slicing a string, it seems, would go into the V8 runtime, try to allocate space, figure out we are out of space, and then do a garbage collection. And that happened 111 times. So again, by looking at the most frequent call stacks leading up to garbage collections, you can often figure out what your application is doing, what it's allocating that would cause the garbage collection to take long or to happen frequently. And I mean, eventually, all garbage collections are caused by allocations. You allocate memory, and at some point, the garbage collector kicks in. So this is a good way of figuring out which allocations often cause the garbage collector to kick in. And again, what you do with this information, you probably want to try get rid of some of these allocations, maybe reuse some of these objects. That's sort of the general strategies you'd use. We don't have time to explore this specific piece of code, but slicing strings is naturally an operation that produces a lot of garbage. You have the old string, and then you produce a new string out of it, and that's a whole new allocation that has to happen. I want to show you just one more scenario. I have two, but we only have time for one, so I'm going to show you the more useful one, I think. And that's a demo which focuses on your app's interaction with the operating system. So there's some kind of weird error that you're getting, and you suspect it's not coming from within your actual JavaScript code. It's coming from interactions with the operating system. And we're going to use a couple of tools here, but I actually want to spice it up just a tiny bit and use an extra tool for this. So if I switch to my terminal here for a moment, I'm going to just do this. Yeah, it's supposed to kill the Node process first. That's interesting. Port 2000 is already in use, even though I've killed Node. What else could be using port 2000? Well, I don't want to waste a lot of our time, so I'm just going to go through the slides anyway. But yeah, what I wanted to add is just one other tool, which I can actually run regardless. And that's a tool called Syscall, which I want to show you even though the app is not actually running. So Syscall is a tool that sits there and looks at all the system calls a particular process or the whole system is making. And system calls, as you know, are just arbitrary interactions with the OS. So it includes reading and writing files, creating processes, sending data over a socket, receiving data over a socket, scheduling switches between threads and processes, waiting for something, a bunch of different things. So Syscall is a BPF-based tool which traces system calls and prints out a summary of the most frequent system calls getting invoked. And that summary can be made available on a per process basis or just a system-wide basis. And if you look here, it would seem that while the system is completely idle, the close syscall is the one that's getting invoked most frequently, so 33,000 times during my recording interval. The reason I'm showing you this is that syscall is a very useful way of sort of characterizing your workload, characterizing what your system is doing as a whole. So you might have a million lines of JavaScript inside, but looking at the interactions with the outside world can often give you a good idea of what the system is doing. Is it doing lots of network I/O? Is it doing lots of file system accesses? Is it just sleeping a lot? Is it forking additional processes? Gives you a general picture of what's happening on the system. In our specific example, which is illustrated here on the slides, I just hit a certain endpoint, and I get this beautiful HTML back that says an error occurred, or maybe more specifically, an error occurred while opening a file. And that's kind of what you have to work with. So again, workload characterization like this with syscall can give you an idea of what the process is doing, like what, again, which system calls are getting invoked, and possibly leading to an error. Specifically, once you know it's a file problem, you're trying to open a file and failing, there is a tool called OpenSnoop that you can use. And that's a tool designed for file operations. It will print out a message when you try to open a file, and optionally it has a filter only for failures. So only print a message when I try to open a file and fail. And it tells you which file I'm trying to open, so here it is, and the error I'm getting. And error 2 on Linux is file not found. So it looks like this file just doesn't exist. But I mean, it could be something else. Maybe the file is already open. Maybe the file, I don't have permissions to read it, or it's some other thing like that. So OpenSnoop can filter out your file opens for you and print out failures. So I only have 30 seconds left, so I'm going to skip over my last example here. But just to give you a very, very general idea of what it was, eventually we get to a point where we could take a running database engine and print out all the queries as they get executed. So we take MySQL or Postgres, or you could potentially adjust it to other database engines as well, and we just, in production, print out all the queries executed by that database. So that, again, is not exactly Node.js specific, but it's obviously very, very useful. I assume a lot of you have some kind of database that you're using alongside with your Node app. So if you're interested in that, just take a look at the slides. So just jumping to the summary, I wanted to show you a couple of different approaches for profiling Node apps in production. We started with the V8 profiler, which is kind of built in and nice and cozy, but it's very, very limited. And you need to launch your Node process with the profiler attached in the first place, so that's a little limiting. Then we talked about perf and what perf can do in terms of recording CPU information, CPU usage. And then we switched over to the BCC and BPF tools, and there's a variety of tools there. I only try to illustrate a couple of those, tailored for different scenarios that people hit often with Node applications. I also have up online, I'll show you the link in a moment, I have a bunch of additional examples that you might want to look at, including some networking issues, like a Node app making slow network requests, DNS resolution issues, database issues. So there's a bunch of different things these tools can be used to investigate. So I have some references over here, but this is the important slide. So it has the link to the slides themselves. And that other link over there, the Linux Tracing Workshop, that's a GitHub repo that has a bunch of examples. It has all of my demo code, but it also has lab instructions that you can follow to learn more about these tools. So it's basically a self-contained learning repository that you can use to experiment with the V8 profiler, with perf, with the BCC tools, with everything I've been talking about in the last hour. So if you find it useful, please let me know. If you have any questions, we don't have time right now, but I'll be staying here in the room or outside, so please feel free to come and talk to me. I hope you enjoy the rest of NDC and see you at the party. Thank you very, very much.